the next presentation will be made by Alexander Kilin or Yury Karavaev or Tatiana Ivanova. Are they here or not?
Yeah, we're here. I am Yury Karavaev here. I will present.
Yury Karavaev, please, you may present your presentation. You may speak.
Okay, just one second. So, do you see my screen? Can I start?
Yes, we can.
Okay. So, first of all, thank you for a very kind introduction. And first of all, I have to thank the organizers committee for really interesting program and really perfect organizations of the conference, even in such difficult conditions of restrictions. I'm glad to participate in the Clover conference and present the results of our investigations to community. So today I would share the results of investigations of our group working in Russia, in Ijevsk State Technical, in Kalashnikov State Technical University in Ijevsk and Udmurt State University. And we continue to research of spherical robots, and our current research aimed to description the motion of robots with different propulsion mechanism and find the best algorithm for controlling it. In our laboratory, 4 different designs of spherical robot was fabricated and investigated. On this slide, you can see the figures of them. And also key publications devoted to their robots are given below. There are spherical robots with internal rotors, with internal omni-wheel platform, and the spherical robots of combined type. But first of all, I need to thank some words about the advantages of such kinds of mobile robots. During the video I talk, so it's the last prototype which we have designed in our laboratory, and due to design of all type of spherical robots, they have a symmetrical shape. And most often, all moving mechanisms and elements of the control system are located inside a sealed spherical shell. So this allows to be used such robots for monitoring and survey tasks in an aggressive environment with, for example, high humidity or in presence of dust. Such robots can swim, roll on not only hard surfaces, but also on snow, glass, grass or sand. Spherical robots of some designs can be made from really cheap parts or components. For some tasks, for example, monitoring or using as delivery tool, it can be made disposable. Our present work is devoted to investigations and development of control strategy for precise movement of spherical robots. This task, first of all, isn't connected with practically directly, but can make the process of control much easier and predictable. And the first problem which arises in dynamic of rolling is friction. In our work, we separate the sliding and rolling friction and consider only the system without sliding. That's why we call it rolling resistance or rolling friction. Of course, we have investigated all and analyzed a lot of works related to motion of spherical bodies or rolling bodies on different surfaces. and the dynamics of different mechanical systems with rolling, for example, spinning top, Celtic stone, ball rolling on rotating table, and etc. And the authors describe the dynamics of such systems in framework of different friction models. Some of them can describe and understand some phenomena accompanying the motion. For example, overturn, change the directions of rolling or spinning, lift off, contact interaction. But nevertheless, some of them are extremely complicated and hard to implement it to real control tasks. Our task is development of quite simple model of resistance for rolling bodies, and then consider it during the process of motion planning. Let's consider a simple mechanical system. The ball rolling on the flat surface. The center of the mass of this ball is displaced and is given by vector c. The position of the geometrical center of the ball defined by vector r, and its orientation in fixed coordinate frame defined by 3 orthogonal vectors alpha, beta, and gamma. The ball can roll on the plane without friction. The equation of motion in form of Lagrange equations of the ball, taking into account kinematical relations given in this slide. This is non-holonomic model of the ball. The ball rolls without slipping. These kinds of equations allows us to add internal moment. In our case, there is rolling resistant moment or rolling friction. It's convenient to present this moment as a sum of two terms. Moment prevents spinning about vertical axis, and moment prevents rolling. And this vector of rolling moment lies in the horizontal plane. We suggest both proportional to angular velocity in corresponding directions, and the following task is obtaining the values of coefficients of rolling and spinning frictions. To do that, we have prepared some special experiment. The idea of it is to capture the experimental data. First of all, parameters of motion of the ball, and then we feed this experimental data to numerical simulation and find optimal values of frictions coefficients. You can see on this figure the non-homogeneous ball with displaced center of the mass. The shell of the ball is transparent because we put inside the shell light reflective markers for motion capture system. And when we deflect the ball, it starts when we deflect the ball from the initial position, when the center of mass located in the bottom position, and then release the ball, it starts to oscillate near this position. So on the picture, on the top picture, you can see the trajectory of such motion, such oscillation. And on the right side, you can see the projection of the vertical axis gamma on moving coordinates frame. These data are obtained using motion capture system. So the main idea is to get this experimental data and then approximate the friction moment based on this experimental data. The figures below present the values of the moment and how they change during the motion. Using this data, we analyze the dependencies of friction moments on angular velocity, and by implementation of least square method, we find the best fitting function. we try to fit the linear and quadratic function, but as you can see, the linear function gives minimal standard deviation, and we use these dependencies later for our investigations. The results of comparisons of numerical simulations for obtained from the experimental data, rolling friction coefficients, and real experimental data shows good agreement, as you can see on this picture. Also not only for friction moment, but also for the components of vector gamma. Experimental data are shown here with small blue circles. We also try to implement the proposed model to describe more complicated rolling. On this video, no, wait. On this video, you can see the retrograde motion of the ball, and its motion is more complicated, but our model also describes such motion. On the next slide, I show you the trajectory obtained from the experiments using motion capture system and simulated one. So it allows us to use such model to describe and design the control strategy for spherical robots. Let's consider the simple spherical model, combined type. With it has a pendulum, 1 degree of pendulum, and a rotor fixed on the pendulum. Here are given the equations of motion, and we also use the same model of model resistance of rolling friction. So the main idea is to develop the using the dynamics to develop the elementary maneuver to combining the two steady-state solutions, which we calculated and simulated and integrated using the dynamic equations. I just want to see, we make some experiments, and now I ask you about 30 seconds. I just show the last slide. Here are the experimental data when we design an elementary maneuver to for control action theta. It's the angular position of our pendulum, and we bring the rotor from the rest position to given, and in this way our robot accelerate from the rest position to given velocity. And here are also simulated data at experimental one, which shows that our model works in general, but some deviations are the reason of such deviations are errors of fabrications and also processing errors that can be more improved. So some conclusions on this slide, and I try to answer your questions. Thank you for listening.
Thank you for your good presentation, and I ask all participants who has a questions. Go ahead. So I ask you a short question. What do you think? How will your robot will movement when the plane will be inclined? Do you understand?
So yes, I understand. Thank you for your questions. So of course there are some limits angle on which our robots can move. but it depends on the size of the robot and of course of mass and inertia parameters of the robot. But of course there are limits, and we can but we can take the inclination of the plane into account, and not only take into but also plan the control action taking into account the inclination angle of the plane.
Thank you very much for your
Thank you.
answer.
Thank you.
Thank you.
May I ask
I-
another question, please?
Of
I-
course, open.
Hi, Yury.
Uh,
Thanks for the lecture. Sorry that we could not meet in person this time, but looking forward to have this chance on some other conference. And I've got questions. First one, it seems that you are doing great with all mechanical things and mathematical things. How about onboard sensing for this robot?
So thank you for your question, Yury. So we design our robots and control system for our robots such to guarantee all characteristics or parameters what we need to realize. For example, if we need to realize given angle of or torque for the motor, so we put inside the sensor to and make some feedback for realize this motion and this characteristic. But of course, when we go in the future to practice more in the practice, we can use different sensors, not only for guarantees and mechanical characteristics, but also EMU, cameras. We have made some tests with the sensors, but it's not a topic of this paper. Maybe in future I share the results of
the time is over. The time is over.
Okay, I will ask another question in the chat privately.
Okay,
Yeah, and
thank you.
the-
Thank you. Sorry.